Hi, this is Professor Pradyot from Leadib Academy, and we are discussing basically the video solutions of IBDP Chemistry SL Paper 2, November 2019. So interestingly, we are not discussing only the video solutions of this question paper, but interestingly, we are discussing the underlying concepts so that you people will get a deeper understanding, okay, of the concepts. And interestingly, we at Leadib Academy have prepared the courses for these subjects like chemistry, physics, maths, etc. And we have uploaded these courses on our website. Okay, so please do visit our website www.leadibacademy.com and you can subscribe to our courses. Okay, so let's begin our story with a question number 5. Okay, copper forms two chlorides, copper 1 chloride and copper 2 chloride. A1, state the electron configuration of Cu plus. Okay, Cu plus. So how we should approach? First, let's look into the copper ion. Okay, not copper ion, copper element, which is the neutral. Okay, and this is basically its, okay, let me put it, this is its proton number. Z is equal to 29. Okay, we can very well refer to the periodic table of the data booklet and you will find its atomic number is 29. Now what is the interesting about copper? Okay, copper is like a favorite element for us asking in the exams. Why it is so simple? So interestingly, while doing the electron configuration, after 3p6 we get 4s. Okay, so ideally the electron configuration, because up to this if we observe very carefully, we have completed 18 electrons, okay, up to this, and we need to fill up additional 11 because total is 29. Okay, now which is the next orbital which comes as per the Aufbau principle in terms of the increasing energy level? Obviously, you people have rightly said it is 4s. So that means we will fill up in s orbital, we can fill up 2 electrons, and then so we have consumed now out of 11 2 and balance are 9. So those will be filled up in the d orbital because d orbital can accommodate maximum 10. Okay, now comes the problem. Now what is that problem? So let me show you with this diagram. Okay, 1 2 3 4 5. Okay, and let me put the electrons. So 9 electrons, these are paired one. Okay, and this is how it will look like. Okay, 9 electrons. This is for 3d9. Now you can easily see that there is only 1 electron which is missing to complete the symmetry, what we call a completely filled up d orbital, completely filled. Only 1 electron is missing, filled up d orbital. So what happens? This element or nature is very, very intelligent. It says that let me sacrifice, let the 4s sacrifice its 1 electron and that would be sent here. Okay, and then because of this now the 4s will have 4s1 and d will have 10, and that's the reason that this is the configuration. Okay, very interesting one. Okay, so the actual configuration of the copper element, we are not yet reached the copper ion. Okay, so it becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d10. Now another interesting part. Okay, once this one has been filled up, okay, the filling up of the electron has been completed. Now what happens? This is very important. 2p6, 3s2, 3p6. Initially, the 4s was on the lower orbital, lower energy as compared to 3d while filling up. But once the filling has been completed, okay, it goes back into its routine. Routine means, okay, that means 3d will be here and 4s will be in the outermost. Okay, 4s will be outermost. Simple. Now, so whenever we want to take out one electron, because Cu plus means what? Simple. Cu plus means we need to take out one electron to bring one positive charge on the copper ion. It is the copper ion. Or to be very specific, cuprous ion or copper 1. So how to make it? Simple. Which is the outermost? This one. So it will be taken out. Okay, simple. That means 4s will not have any electron, and what will be left with this? 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10. Simple. Okay, extremely simple. Okay, so final electron configuration is this. This is what is very, very important. So what we have learned, the two things: copper's interesting electron configuration. That means the first, even though it should have been 4s2, 3d9, but just to bring the symmetry, completely filled up d orbitals, one electron gets shifted from s orbital to d orbital. Okay, so that d orbital is completely filled up, 3d10. Okay, and then the second thing, interesting one, that after this filling up of the electrons, again the normalcy is retained. That means 3d will get lowered, okay, and it will come inside while 4s1 will be outside. So when we are trying to take out electron, it is being taken out from the outermost 4s orbital. This is the crux of the story. Okay, and why I'm telling, because this is where the confusion starts. Okay, so while drawing this one, first of all, it should be clear that the configuration itself is not 4s2 and 3d9. Okay, that is most important. Okay, so it is 4s1 and 3d10, and while taking out the electron, you take out from the 4s. Simple. Okay, very, very interesting one. Okay, question number 5A2. Interesting question. Okay, so it is being asked, copper 2 chloride is used as a catalyst in the production of chlorine from the hydrogen chloride. And they have given the reaction. Calculate the standard enthalpy change, delta H naught in kilojoules for the reaction using section 12 of the data booklet. So we are aware of that delta H for the reaction, okay, for the given reaction, okay, this is delta H naught, okay, for this reaction is equal to, okay, you take summation of all the products, okay, delta HF naught, okay, this is for the products. You sum all this one for the, okay, for their formation minus summation of heat of formation for all the reactants. Okay, this is the formula for calculating the enthalpy change for the reaction, and this is a standard enthalpy. So now understand very carefully, what are the reactants? Please remember, now let me highlight this. In this case, there's a chlorine is the reactant and a water, okay, Cl2 and H2. But very important that chlorine is in its standard state. Why? Because chlorine exists like a Cl2. And as per the convention, okay, whenever any element is existing in its standard state, like Cl, chlorine is existing in its standard state, that is Cl2 in the gaseous form, it would be treated as zero. Its enthalpy of formation is zero. Okay. Similarly, you can observe on the reactant side, oxygen is there in its gaseous state, standard enthalpy change is zero. This is very, very important to understand. So let me this one mention delta HF naught for O2 and Cl2 is equal to zero. Okay, this should be clear, because otherwise you may start looking out for in the data booklet and then you will get confused because it is not going to be there. Simple. Okay, so it means that what is left is now, okay, only H2O. So there are two H2O molecules. So let me put it 2 times of, okay, H2O. Okay, let me write it. Okay, sorry, let me remove this and mention 2 of, okay, for H2O minus 4 times HF naught for HCl. Okay, simple. Now what we'll do, we'll go to the booklet, data booklet, and let's see. So let's see for the water. For the water, okay, so let's see whether water is in the gaseous form. So we have to use appropriately the steam part. Okay, so let me zoom in. Okay, so you people can easily see that steam, gaseous, okay, minus 241.8. Okay, and let's see hydrogen chloride in the gaseous minus 92.3. Okay, so it simply means that let's put these numbers, okay, very clearly. Oops, sorry. Okay, so let's put it for water. It is minus 241.8 minus 4 times, okay, hydrogen chloride, that is minus 92.3. Let's take out the calculator. Okay, and you should get, okay, very, very simple, minus 114.4 kilojoules. Okay, this is going to be delta H naught R for this reaction. Extremely simple, just you can use it. Okay, so what are the learning points? First of all, the formula enthalpy change for the reaction is the sum of the enthalpy change for the formation of all the products minus reactants. And second, whenever any element in its standard state, okay, standard state, then its enthalpy of formation is 0 by convention. Simple. Okay, very, very simple. Hope this is quite clear and very simple. Okay, 5A3. The diagram shows the Maxwell-Boltzmann distribution and potential energy profile for the reaction without a catalyst. Annotate both charts to show the activation energy for the catalyzed reaction using label EA catalyst. Okay, so first, very, very interesting question. Okay, Maxwell-Boltzmann distribution. So what it indicates, very simple, how kinetic energy has been distributed amongst the given sample of gas molecules. Okay, it just gives the kinetic energy distribution, and we know each and every molecule is not going to possess, okay, the same kind of a kinetic energy. So there is going to be a distribution, like how you get in a math exam. Okay, let's say a class of 100 students, not everyone is going to get, let's say, a 90% grade. Okay, some may be getting 40%. Some of you are like brilliant students like you, getting more than 85 or 90%, something like that. Okay, so there is something that there would be average, that maybe 65% grade will be obtained by majority of the students, maybe 35% of the students may be getting, let's say, a 65%, something like that. Okay, and this gives the basically distribution. Now, important that whenever we put the catalyst, okay, now first understand what is given. This is activation energy. What do you mean by activation energy? Activation energy means that is the energy which is required by the reactant molecules. Okay, minimum energy that is required by the reactant molecules to start or initiate the reaction. Simple. It means that any molecules which are possessing energy less than the activation energy, they are useless for carrying out the reaction. Okay, unless until they possess that minimum energy, then only they are useful. Extremely important concept to be understood. Okay, so if molecule possess the minimum energy, that is activation energy, or more, obviously they will be useful for the reaction. Okay, now comes the interesting part. Okay, so in this case what is happening is that this is the fraction of molecules which are possessing energy higher or equal to activation energy. That means this is what is the useful molecules, I will say. Useful, okay, molecules to start the reaction. Okay, now comes the interesting role. Whenever we put the catalyst, what catalyst does? Catalyst reduces this EA, okay, and it gets lowered. So I'll say it is like this, EA catalyst. So it has lowered it, okay, it has shifted to the left hand side, it has been shifted to the left hand side. So because of that, now interestingly, we are getting these additional molecules which otherwise were not there. These are additional useful molecules because of the addition of catalysts. Additional useful molecules. I'm using the term useful for your understanding, because now they are also going to participate to initiate the reaction. Otherwise, they were useless without adding the catalyst. So this is exactly what catalyst does. It brings in the additional molecules in picture. Okay, so this is for, okay, this is how we can think of the Maxwell-Boltzmann distribution. Now comes from the potential energy. What catalyst knows? We know very well the definition, that after adding the okay, it basically chooses the path having a lower activation energy. So what could be that path? The path could be like this. Okay, this is the alternative path. Alternative reaction path with lower EA. Okay, so we will term this now as EA with catalyst. Simple. It has taken now a different route. Okay, the reaction is same, but now it has chosen a different route, okay, to complete the reaction. And why it is this one different? Because now it is going to have a lower activation energy. So that is how the reaction speeds up. Okay, extremely simple to understand. Both these diagrams are extremely useful. Maxwell-Boltzmann and the potential energy. Hope this is quite clear and you must have found it interesting. Okay, 5A4, explain how the catalyst increases the rate of reaction. We have already seen, okay, that by introducing the catalyst, the activation energy goes down, it gets reduced. So I'll say EA catalyst. That means we are going to get these additional number of molecules which will be now contributing to the rate of reaction. Okay, simple. So this we can explain using the Maxwell-Boltzmann because the reduction in the EA. So I'll say additional molecules, okay, possessing energy greater than or equal to EA catalyst. Okay, that means because of this we are going to get the additional molecules, whatever I have shown in the dotted. If you want to explain using this potential energy, we have seen that it chooses the alternative reaction path having, okay, a catalyst activation energy lower than the original. This was the original, okay, this is EA, and now it has been lowered. So we'll say the second weight is alternate reaction path having EA catalyst less than EA, which is original. That's this. I'll explain it very clearly without catalyst. Okay, simple. So there are two ways, okay, and that option is left to you. You can explain, you can understand from both this one, okay, Maxwell-Boltzmann as well as this potential energy profile. Both are extremely easy and very, very useful and very effective. Okay, simple. Question number 5B appears to be interesting from stoichiometry. Solid copper 2 chloride absorbs moisture from the atmosphere to form a hydrate of formula CuCl2xH2O. A student heated a sample of hydrated copper 2 chloride in order to determine the value of X. Following results were obtained. Okay, so let's try and visualize this. That is always the best bet. Mass of crucible. Okay, so let's take this. Okay, I'm just showing. This is the mass of empty crucible. So, okay, this is equal to 16.221 gram. Then what we have done, the next step is we have put, okay, the hydrated okay 18.360 gram, and then sorry, and the last, okay, let me show with different color just to make a difference. Okay, so this is hydrated anhydrous, and this is empty. Okay, and let me put the numbers for this. It's 17.917 gram. Now understand that this is basically whatever is this is including CuCl2 XH2, while in this case it is only CuCl2. Why? Because now the water has been driven out. Okay, when we heat, okay, the water which is attached, that is XH2O, leaves. Okay, it gets removed, and whatever is left over with this. Okay, very, very straightforward. Okay, now understand. So how to calculate now the mass of water? So the mass of water, it's simple. Okay, it is going to be the difference between the hydrated and anhydrous. Simple. It means that it is 18.360 gram minus anhydrous, that is 17.197 grams. And what about the mass of anhydrous or mass of only CuCl2? Simple. It is going to be 17.917 gram minus the mass of empty crucible. This is the crux of the problem. If you have understood, then it is simple. Okay. Now, what is the next step? Okay, so let's quickly calculate this. Let me take out my calculator. Okay, and do the quick calculations. 18.360 minus 17.917. So this gives me 0.443 gram. And let's do this. 17.917 minus 16.221. So this gives us 1.696. Okay, now let's move on. What is the next step? Now we will calculate moles of water or moles of H2O. How to do this? Take the mass, that is the mass of water, that is 0.443, divided by the molar mass. This we can easily obtain from using the data booklet, okay, and we can do the calculations. Then what about the moles of CuCl2? Okay, it would be 1.696 divided by, okay, this would be divided by 134.45, that is the molar mass. Okay, so let's do this calculations. Take out the calculators, and I think you should be getting this and this. Okay, that means the moles are in this ratio. So we can really now look into this, quickly do the calculations. Okay, it means they are in the ratio of 0.0246. This is pertaining to H2O divided by 0.0126. This is for CuCl2. I think we should be getting roughly around 1.95, which we can very well round it off to 2. Okay, so therefore we can say X is equal to 2. What does it mean? It means that the formula for that hydrated one is CuCl2 2H2O. Okay, very, very simple. CuCl2 2H2O. Okay, it was a good quality question. So understanding how to calculate, okay, basically they had given us indirectly the mass of water and CuCl2. Okay, but it was a good quality, but very, very simple. Okay. Question number 5C. An electrolyte cell was assembled using graphite electrodes and connected as shown. And they are showing molten copper 1 chloride. State how current is conducted through the wires and through the electrolyte. Okay, very, very simple. Okay, so we know very well, okay, that in the wires, okay, when we take any wire, okay, that means we are talking about the metallic wire. So what happens in case of metallic wire? There are a lot of free electrons. So these are electrons. Okay, I'm just showing electrons with the negative charge. So what happens that whenever we apply electric field, okay, it is like this, that we apply a battery or EMF, okay, these electrons, they start moving, okay, and that means this is due to movement of free electrons. So whenever the current, okay, flows, okay, through the wires, this is due to movement of free electrons. Because we know, as per the metallic bonding, there are a lot of free electrons. The metal ions are basically submerged in the sea of free electrons. So those electrons move because of this application of this battery or EMF. But in this solution, okay, there are a lot of free ions, because when we say Cu1 chloride, that means there is going to be ions of Cu plus and Cl minus. So what happens that, let me show few ions. Okay, so there is going to be a copper ion, that is Cu plus. So that is going to get attracted for the negative electrode, and similarly there would be Cl minus ion, which is going to get attracted towards the positive electrode. Okay, so these are what we call cations and anions. So in this case, through the solution, due to movement of cations, that means positive charge, and anions. Okay, so there are two aspects: through the wires, free electrons; through the solution, okay, the cations and anions in the solution. Okay. So in this case, cations are Cu plus and anions, they are Cl minus. Simple. Okay, extremely simple question. Hope this is quite clear. Okay. Question number 5C2, write the half equation for the formation of gas bubbles at electrode 1. So understand, sorry, let me, this one. So they are asking what kind of a gas is going to get formed. Okay. So first understand that it is Cu1 chloride, that means Cu plus and Cl minus. These are the ions. This is cation, positively charged, and this is anion. Okay, very simple. Now anions, they are going to get attracted towards the positive terminal, that means on this, okay, on 1. So it is very clear that on electrode 1 it is going to be. Okay, anodes means electrode 1 and anion, that means this has to be anode. And we know very well, we have seen many times, or you need to remember that anode means oxidation. And what is mean by oxidation means loss of electrons. So please remember, Cl minus, it is the anion, negatively charged, that means it is going to go towards the anode. Anode means oxidation, irrespective whether it is an electrolytic or voltaic cell, okay, or electrochemical cell, always oxidation. Anode means oxidation, and oxidation means loss of electrons. So what? Let now start writing the equation. Simple. So there is a Cl minus ion which is going to lose. Okay, so we'll take 2 Cl. Okay, let's take only 1. So 1 atom of chlorine and we'll get 1 electron. So now what we will do, we will take 2 Cl atoms, okay, such kind of a thing, and we will get Cl2. Okay, so just to balance this, so what we can think of, that instead of writing like this, it is better that we will write like 2 Cl minus going to give us Cl2 plus 2 electrons. Okay, this could be the half equation at electrode 1, that is nothing but anode. Okay, so basically Cl2 gas, that is a chlorine gas, will evolve. And obviously you must have guessed it, on 2 it would be Cu, copper. Okay, very simple. Hope this is quite clear and simple also.